Hello and welcome back to another webinar for Ansys Rocky. So today we'll be having a discussion on some of the more advanced features of the software. Primarily, the intent of what I'll be talking about is to showcase how we can effectively extend the basic capabilities of the software and to develop improved workflows and outcomes for our simulation. So today's session is the third in a series. We've had some previous sessions on Rocky for heavy machinery, which included an element of multi-body dynamics and coupling with FEA. We've also had another session on Rocky for conveyor and transfer chute design. And so you'll find these recordings on either as blog posts on our LEAP website or the recordings on our YouTube channel. So to facilitate today's discussion, we'll be covering three main topics. So we'll start off with a walkthrough of Rocky's APIs, moving on into the integration with OptiSlang, and finishing up by touching on some of the GPU-based considerations. Now, do note that, as you can imagine, since this is a 40-minute session, as far as the list of advanced features goes, this is not extensive. So there's plenty more to come, and we'll likely be covering some of the more specific topics or niches in future webinars. And in fact, just on that, if you were keen on seeing anything in particular or had any questions or issues, please feel more than free to reach out to myself directly or the support hotlines as you saw before. Okay, so to kick things off, I wanted to cover Rocky's application programming interfaces, or APIs. At a very high level, an API in this context is essentially just another way, or a code-based way, to interface with and interact with the software. So users can extend the capabilities of the software through customization of both the DEM solver and the application itself. So to be specific, Rocky's API can be split into two types, the Solver API and the Pre-Post API. As the name suggests, through the Solver API, users can access and manipulate solver-level data to either implement new models or customize existing ones. Now, on the other hand, with the Pre-Post API, users effectively have access to pretty much anything you could do through the GUI and a little bit more. And this means that we could set up, solve, and post-process a given analysis by means of scripting. So there are now possibilities to automate many different types of tasks and handle the simulation data in ways that you couldn't do through the standard GUI. But I'll start by talking about the Solver API in a little bit more detail. We can use this, the Solver API, through the Rocky Software Development Kit, or the SDK. And we can use this to create our custom models. And these are implemented in Rocky as what we call as modules, which are basically compiled libraries which attach to the Rocky solver. Through this, we could implement our own custom adhesion model, for example, introduce maybe some new physics into the simulation. We could consider something like radiative heat transfer maybe, or use carefully defined contact and maybe motion-based conditions to speed up simulations. And we'll actually look at an example of this shortly. But some of the key benefits of the Rocky SDK is that user-generated or modified models will basically run as fast as built-in Rocky models, which we can actually see in the top right figure, which compares the solve times for implementations of the default contact model. So it uses the same data structures and an identical computing flow, which means that both standard Rocky and API models will maintain the same simulation time and the same memory consumption. Now, fortunately, it's actually very easy for users to get started with using this feature through access to an extensive modules repository through the customer portal. And this is also accessible through the GUI. And we'll be going through some interesting examples of what's available, which again, won't be extensive because there's actually 44 ready to use modules, and we'll go through maybe 4 or so of them. But the first one I wanted to look at is the bond model module, which is implemented as an alternative adhesion model, basically. This allows you to create bonds between neighboring particles with a specified normal and tangential strength limit, Now, once these limits have been exceeded in the model or in the simulation, the bonds will break and the material will no longer be bonded. And so the bonds created by the bond model exert both elastic and viscous forces, and the moments based on relative motion between the constituent particles in that bond. So applications of this will include things like drilling or cutting into a solid or brittle material such as rock and concrete, which you're seeing on screen there. Now, similarly, in a similar manner to the bond model, we can actually implement another type of adhesion model, which represents the effect of the presence of liquid films over the surfaces of particles. To be more specific, the liquid bridge model will calculate and apply the capillary and viscous forces that a liquid bridge will exert over particles. Now, these particles will be within a certain separation distance threshold. Now, as the simulation progresses, the redistribution of liquid mass is tracked through collision events. And we can actually also combine this with alternative modules, where these modules/models will essentially consider many different types of physics, essentially. So we can combine this with something that will create a region where essentially virtual liquid mass is injected, along with one that handles the evaporation and subsequent deposition of the dried solute on the material. So through the Solver API, we could introduce various different conditions which can trigger particles to basically be frozen or locked in place, effectively switching off motion calculations, while separately, we can also remove particles from contact detection altogether, which you can imagine is going to greatly reduce the computational demand in a given simulation. Now, these features can be, of course, used to efficiently speed up simulation times by reducing, as I mentioned, the workload of the solver. In these examples on the left, particles are frozen based on a prescribed cutoff velocity to model deposition on the left, as well as based on location on the right. So we're only keeping motion switched on for the materials within the active area of the simulation. So we can consider alternative physics, as I've mentioned before. So magnetic and the ferrous-magnetic force modules enables users to essentially import magnetic field data as point clouds into Rocky, which will define an additional body force acting on particles. The last example I had on this shows the implementation of empirical-based erosion models, which will consider the impact angles, impact velocities, as well as, of course, material and particle properties to calculate the cumulative eroded mass due to particle boundary collisions. So we can use this as an alternative to the inbuilt wear model, which is based on Achard's law. Okay, moving on to the pre-post API. This is essentially a Python-based tool for scripting and automation. So users can create custom scripts which can be executed both prior to and after the solver has run. From a pre-processing perspective, we can use this tool to both build a project from the ground up, or take an existing project, make modifications, and run the solver. Once the model is solved, again, we can use a Python script to handle and manipulate the data for more advanced post-processing. You may have actually seen this being done before in a previous webinar where I actually used a script as part of my investigation of belt wear characteristics. Altogether, the Python API brings users the benefits of being able to build repeatable workflows, of course, automate repetitive tasks, and ensure quality control between simulations. Now, there are different ways that we can use the Python API in Rocky. So I think it's probably a good idea to just jump right in to Rocky and do some stuff.